A tiny quantum clock reveals a billion-fold energy puzzle. Researchers at the University of Oxford have uncovered a surprising twist in the physics of timekeeping at the quantum scale. Their new experiment shows that the energy required to read a quantum clock is up to 1 billion times larger than the energy needed for the clock to operate. The findings suggest that the act of measurement, not the clock mechanism, creates most of the entropy that gives time its forward direction. The study, published on November 14 in Physical Review Letters, offers a new way to think about energy, information, and time in quantum devices. If you like my content and want to listen more interesting science stories like this, then subscribe my channel. And don't forget to like and share this video with your friends and colleagues. Why timekeeping gets strange at quantum scales. Every clock, from a swinging pendulum to an atomic oscillator, depends on processes that are irreversible. This irreversibility is tied to entropy production, which defines the arrow of time. But in the quantum world, these irreversible steps become extremely weak or nearly vanish. That presents a challenge. If quantum systems produce very little entropy, how can they reliably mark the passage of time? Future quantum sensors, quantum navigation tools, and nanoscale computers will need clocks that operate with extremely low energy consumption. Yet, until now, the thermodynamic costs of timing at this scale were poorly understood. Measuring the true cost of time. The Oxford-led team set out to separate two things. One, the energy cost of the clock itself, and two, the energy cost of observing it. To do this, they built a tiny clock based on a double quantum dot. In this system, a single electron hops between two microscopic regions. Each hop serves as a tick. To read the ticks, the researchers used two methods: measuring ultrafine electrical currents and detecting shifts in radio frequency signals. Both techniques convert fragile quantum events into classical signals, an unavoidable step known as quantum to classical measurement. The billion-fold surprise. When the team calculated the entropy produced by both the clock and the detectors, they found something astonishing. The detectors consumed up to 1 billion times more energy than the quantum clock itself. This result overturns the long-held assumption that measurement costs can be ignored in quantum systems. More importantly, it shows that measurement is the main source of irreversibility. In other words, the forward flow of time emerges primarily from the act of observing a quantum process, not from the quantum ticks themselves. Implications for quantum technology. This discovery reframes how scientists think about designing quantum clocks and nanoscale devices. Instead of focusing solely on improving the quantum components, the real challenge lies in making measurements more energy efficient. Lead author Natalia Ayres explains the shift. Quantum clocks were expected to reduce the energy cost of timekeeping, but our experiment reveals the opposite. The cost of reading out the clock dominates everything else. Interestingly, the researchers suggest that this large measurement cost may not be purely a drawback. Because the detectors use more energy, they also capture more detailed information about each electron hop. Not just tick counts, but the nuances of the clock's fluctuations. This could ultimately yield more precise timekeeping. A new connection between energy, time, and information. Co-author Vivek Wadia emphasizes that the entropy generated during measurement is the fundamental thermodynamic cost of quantum timekeeping. Understanding this cost could help scientists design autonomous quantum devices that mimic the efficiency seen in biological systems. Co-author Florian Mayer highlights the deeper implications. By showing that measurement, not just ticking, drives the arrow of time, we reveal a link between the physics of energy and the science of information. A new roadmap for quantum clocks. The study suggests that future quantum technologies, from clocks to nanoscale computers, will need to rethink not just how information is stored, but how it is read. If researchers can learn to measure quantum systems more efficiently, they could build devices that keep time with unprecedented precision while consuming far less energy. For now, this tiny quantum clock exposes a giant mystery. In the quantum world, it is not the taking that costs energy, it is the act